to talk to us about can the flow behind a weak shock Mach reflections be shock-free?
Thank you, Susan.
Tell
Thank
us.
you very much for the invitation. Yeah, this is sort of a retrospect. In some ways, this will be a retrospective talk about a problem that's interested me for a long, long time. In fact, my PhD thesis addressed some of these questions to do with sort of asymptotics for shock, diffraction, and reflection. And I don't know how far I'll actually get. I'll give a bunch of the background, and maybe I won't get to any details about the actual topic about this question of whether Mach reflections can have shock-free flows behind them. But it's just a small attempt to try and do some analysis on these problems, which is extraordinarily hard. So let me just start with a review about shock reflection. So the basic shock reflection problem, or one of the basic ones, self-similar shock reflection. You have a wedge here, maybe with some half angle theta W. You have a shock that comes in, hits the wedge, and then reflects. So at the instant it hits the wedge, you have this sort of picture, and the shock has a certain Mach number. Mach number 1 would be small amplitude limit, and so then the question is what happens. And for a given gas, let's say for a given value of gamma ratio of specific heats, you'll have compressible Euler equations describing the flow. And then you have this initial data, which is self-similar under expansions, you're rescaling x and y. So the solution, then you have solutions of steady compressible Euler equations. I'm not going to write them down. And the solution is self-similar. It's a function just of these coordinates x over t and y over t. So it's often called pseudo-steady in the engineering literature. Now I should say, and then you see some reflection pattern coming out. And there's two sort of basic, simplest patterns. So one is sort of regular reflection, which is some, let me just draw the upper part, the wall here. So you see the instant shock, you see a reflected shock, and you see a diffracted wave like this. So it's like a linear pattern of the wave equation. And then, so this is regular reflection. And then you also, in different parameter regimes, have what's called Mach reflection. So there you typically see a pattern like this. This is incident, this is reflected, or diffracted if you like, and then there's a Mach shock. So the sort of reflection point moves up off the wall, and you get this picture with a triple point where the instant, diffracted, and Mach shocks all meet. So I'll show you some more pictures in just a second. I will comment, Euler is maybe a little unphysical in the following respect, that in these self-similar solutions, the moment the shock hits the wedge, the whole pattern, question, yeah.
Why does the incident bend towards the...
So the instant bends because I'm not good at drawing straight lines. So this is supposed to be a straight line, but then the Mach shock will bend because there's a non-uniform state behind it. That answer the question? So as I was saying, in some sense, there's an issue with Euler because the whole pattern just suddenly appears, however complicated the pattern is. So it's a bit like Athena springing from the head of Zeus, fully formed, if you know that myth. But roughly you see this regular reflection in sort of a more linear regime. So weak shocks, large angles. This Mach reflection is sort of a fully nonlinear type of thing. So here's an experimental interferogram of a regular reflection. So you can see here's the instant shock, here's the reflected shock. It's a constant state here, constant supersonic state here. And then here's the diffracted wave that's generated off the corner of the wedge. So this, this type of reflection has been analyzed for quite a while now. So originally, there's some work by Koenig, Kiefitz, and Kim for a transonic small disturbance approximation, which is I'm going to talk about in just a minute. And then there's a huge series of works by Chen and Feldman for potential flows. So you sort of ignore vorticity and entropy in that work. So this 2018, this is a Princeton monograph of 832 pages on their work. And the only thing I want to say here is for essentially this is an elliptic problem. In this regular reflection, you know, so I should say, these self-similar equations, I should backtrack a minute. The self-similar equations are equations in x over t, which is xi, say y over t, which is eta, and they are mixed type equations. In some regions, they're hyperbolic or supersonic. In other regions, they're elliptic or subsonic. So there's a change of type. Now, in this framework, everything out here is hyperbolic, and you completely know the solution in the hyperbolic regime. Everything inside this diffracted equation wave, the waves are elliptic. So you're solving elliptic equations inside this non-uniform region. So basically, this involves an elliptic problem. It's essentially an elliptic PDE. That's why it's practical in some sense, because you can do elliptic PDEs. Now, it's a very difficult elliptic problem. Okay, you've got a free boundary here for the shock, so you have to figure out the location of the shock. On this sonic line here, the elliptic equations degenerate, so they're sort of parabolic. You have other things like a corner in the wedge that you have to worry about. So it's a very nasty elliptic free boundary value, sort of degenerate elliptic boundary. But essentially, it's an elliptic problem. So it's not what I would call a truly transonic problem, where you have a mixed type equation, which is partly hyperbolic, partly elliptic. And what's happening in the elliptic and the hyperbolic regions is coupled together. All right. Okay. So here's another picture of a shock reflection for a weak shock. This is a weak shock Mach reflection. So here's the incident shock. You can see this triple point. This is the Mach stem down here. This is sort of the reflected shock. And inside here, is the diffracted wave. And at least at this global scale, it sort of looks, you know, supersonic or hyperbolic here, supersonic, hyperbolic here, and then subsonic elliptic inside this diffracted wave. Now, the big question for Mach reflections is the following, the weak shock Mach reflections. This goes back to von Neumann's work at Los Alamos in the war years, where he did a systematic study of, you know, what kinds of junctions you can get between shocks and other discontinuities. And the thing is the following, that for weak shocks, in other words, ones whose Mach number is close to 1, if you do the jump conditions around a triple point, you find it's not possible to get a triple point. Okay, so the issue is this, that if you look at this triple point, you can either go across here and then across here, or you can go across here. So you either jump across the incident and reflected shock, or you jump across the Mach stem, and you find out that there's no state behind there that you can get both by jumping across here or by jumping across here, even if you include a contact discontinuity. And yet you appear to see this triple point in experiments. So this became known as the von Neumann triple point paradox, that the experiments seem to be in contradiction to what you just get from shock conditions and jump conditions. So there were, so it's just repeating what I said, and I should say also, of course, and sort of putting this under the rug a bit, but there's also a contact discontinuity that comes out of the triple point. So you have 3 shocks meeting at a point. The state that you get by going through the incident and reflected shock has different entropy, different tangential velocity than the state you get by going through the Mach stem. So there's actually what's called a contact discontinuity as well from the triple point, where the entropy and the tangential velocity jump. But for weak shocks, that contact discontinuity is very weak, third order in the shock strength. So, and it's sort of going to go, those things will go away in the equations I'm going to show you. So since this time, there were many attempted explanations for this triple point paradox. Why do you see this triple point when it's not consistent with jump conditions for conservation of mass, momentum, and energy? So the immediate resolution is the following, that there's actually an additional expansion fan and tiny supersonic region behind the triple point observed in very high resolution numerical computations. So this was first observed, the observation for full compressible oil was this paper by Vasilev and Tricomi, where they actually see a fourth wave, an expansion fan coming out of the triple point. And in work with Moisy Brio on sort of transonic small disturbance models that I'm going to talk about, we saw there was a tiny supersonic patch, which I'm going to show you in more detail, behind the triple point. And that also leads to the conclusion there should be an expansion fan at the triple point. And I'll show you pictures in just a second. Now, it turns out this structure was actually suggested by Gooderley back in 1947 in a technical report. And, an extra expansion fan, a fourth wave, and the tiny supersonic patch. So it's appropriate, it seems appropriate to call this Gooderley Mach reflection. And the reason it was up in the air is it's so tiny, this structure, that nobody had actually observed it. So it's not that explanation was there, along with many other possible explanations, but there was no evidence really that that was the correct explanation until these numerical observations here. Now, what I also want to say is, this is the immediate resolution, the existence of a fourth wave and expansion fan generated at the triple point. But then there's a lot more questions about leading to a very complex transonic structure immediately behind the triple point that I'm going to show you in just a minute. So let me just go over this somewhat quickly. So my interest has always been in sort of doing asymptotics to try and simplify the problem, and rather than deal with the full Euler equations, deal with various sort of approximations, and in particular what are called transonic small disturbance equations. So here you look at flows whose flow speeds are very close to the speed of sound. And with appropriate scaling, so here's the scaling. So U is the -1, this is the flow speed exactly sonic from right to left, so like speed of sound, flow speed. U is then the perturbation in the x velocity from that sonic speed. So it's sort of like this picture here. You basically have a sonic flow here. So in my convention, it's convenient to do it from right to left. You could do it the other way. And then U and V are like U is the perturbation of the x velocity, V is the perturbation in the y velocity. And they have to be scaled appropriately. The y perturbation the velocity perturbation is smaller than the x perturbation. And so you see, by the way, sorry, I should say this, the U is actually now in this direction. So positive U will actually give you subsonic flow, and negative U will give you supersonic flow. The negative U will add to this to give you Mach numbers, magnitude more than 1. So, all right, so I don't want to say more about the derivation, but what you're led to is this equation, which we call the unsteady transonic small disturbance equation. And it actually goes back to Lin, Reisner, and Seen in about 1948. So this is sort of asymptotics for nearly sonic flows in this limit. So let me just say a few words about it. So if V is 0, so there's no y velocity and everything's independent of y, This guy just goes away. You just get the inviscid Burger's equation. So that's, ut plus half u squared x. So that's the basic equation describing shocks. So if anyone has looked at shock waves, you probably studied inviscid Burger's equation. So this is a sort of two-dimensional generalization of the Burger's equation. You've got now transverse velocities here. So this is a diffraction term. And you could think of this, it comes out of the asymptotics. This is basically an irrotationality condition, that the velocity perturbations are irrotational, and then they're coupled like this. And in particular, this describes glancing weak shock Mach reflections in the limit when the wedge angle is the square root of the shock strength, and both are small. So it's describing Mach reflection of weak shocks by very thin wedges. Okay, so then there was a lot of stuff about deriving that. I maybe won't go into that. Now, this equation probably looks, kind of fairly trivial. I don't know, you just have Burger's equation with an extra couple of linear terms. But as I want to hopefully convince you, it actually leads to extremely complex behavior. And it's, in some sense, it has some of the same fundamental difficulties of dealing with any multi-D hyperbolic systems of conservation laws, for which the general theory is pretty much non-existent. Yeah, question.
What happens to the pressure when you take the limit?
Sorry, what happens?
To the pressure.
So that's a good question, yeah. So the pressure is actually proportional to U, because these are like acoustic waves. In an acoustic wave, they carry pressure variations and velocity variations and density variations, and those are all just proportional to U. So you could also think of U as the pressure. Yeah, good question. All right, and then again with a bunch of asymptotics that I'm not going to go into, the sort of weak shock thin wedge problem is described by this UTSD equation. Let's say we just think about the upper half of the wedge with the following boundary conditions. So initial boundary conditions. And it's maybe easiest if I just show you a picture of those initial conditions. So this is the instant shock. And sort of in the limiting thing, the reflected shock is sort of along this axis here, y equals 0. So U equals 0, V equals 0, that's the state ahead of the instant shock. Behind the instant shock, you get U equals 1. So you can think of 0 to 1, that's the pressure jump. And then there's also a deflection in the angle of the flow. So the flow, zero flow here, the flow gets deflected back down this way and hits this rigid wedge. So the picture is sort of something like this. This is the initial state in this transonic small disturbance model. There's no velocity here, no perturbation here. Then there's a velocity. The flow sort of gets deflected down like this. And then this hits this rigid wall here. And the result is a wave, the reflected wave comes off. So here's a global numerical solution of that initial boundary value problem for A equals 0.5, which is in the Mach reflection regime. So here's the instant shock. You see here's a very weak reflected shock. Here's the Mach stem. They meet at this triple point here. And then there's a large subsonic region where again, it's a mixed type equation in these self-similar coordinates, x over t, y over t. The equations are elliptic in this region, hyperbolic in this region, and hyperbolic in this region. In fact, they're constant here and here. This is the state 0 ahead. This is the state 1 minus a. And that's what you see. Now, again, the triple point paradox is evident here because it looks like you have a triple point here with 3 shocks meeting at a point. When you analyze the jump conditions, there is no such configuration. All right, again, because there's no single state that you can get by going across instant reflected to this state and also just going across the Mach stem. So this appears to have a triple point, but that's theoretically impossible. So it's exactly the von Neumann triple point paradox in this UTSD limit. So what's the explanation? So here, let me show you a close-up. So note, by the way, this, you can see the x-axis here. It's kind of going from -3 to 2. These computational boundaries are there because you have to use not x over t, y over t, but basically you have to use, if x over t is xi and y over t is eta, you actually have to use the coordinate xi plus 1/4 eta squared in the numerics to get things to work. So the parabolic boundaries are just a function of how the numerics is done. All right, so, okay, xi is going from -3 to 2. And let me show you a close-up that Alan Tesdell, my former PhD student, did in these numerics, what's going on near the triple point. Okay, so first thing I want to notice what x over t is. It's going from 1.005 to 1.01. So this width in x over t is basically 0.005 wide. So it's an incredibly, if you go back here, it's basically a 0.005 width around this triple point. Now, Alan did incredible numerics on this. So it's sort of, it's iterated towards steady state because in self-similar coordinates, this is steady. And then what he would do is he would interpolate a larger scale solution to a smaller scale solution in a region around the triple point. And I think he did that about 8 times to generate the solution I showed you before. So it's really, really remarkable piece of work. Now, what does this show you? Well, it shows you the following. Okay, this is the state ahead of the instant shock. This is the state behind the instant shock. This is the reflected shock here. And the dotted line is the sonic line, the place where the self-similar equations change from hyperbolic to elliptic, or supersonic to subsonic. And what you see here is the instant shock, the reflected shock, collide at this point, but they generate an expansion fan. So the picture looks something like this. I'll draw a schematic in just a second, but these two shocks collide, they form the Mach stem, and at the same time, they generate an expansion fan, which is not a discontinuity. It is typical expansion fan like you might see for Berger's equation. And the point is, if you go from here to here to here and across the expansion fan, that's compatible with going from here to here across the Mach stem. But without that fourth wave, that expansion fan, there are no solutions of the jump condition. So I'll probably say this again, but it's a bit like what happens in if you do unsteady 1D gas dynamics, you see this kind of phenomenon. You have one shock overtake another shock. They merged in the same family. They merged to form a shock in the same family, but then they also generate a backward reflected expansion wave coming off in the other direction. And that's sort of what's going on here. Now, notice that the sonic line is dashed. So you see this structure here. Now, what's going on here is the following thing. This expansion fan actually pushes out this sort of tiny supersonic bubble behind the triple point. So inside this bubble, I mean, at the global scale, everything behind here looks elliptic, but actually you see there's this tiny supersonic patch here pushed out by the expansion fan when the equations are hyperbolic. And one of the basic ideas here in transonic flows is, you know that boundary value problems for hyperbolic equations on closed regions are overdetermined. You typically don't get solutions for boundary value problems for hyperbolic equations. And that's sort of what you have here. You have this closed bubble. And what is going on is this expansion fan hits this sonic line, it reflects off as a compression wave, it forms another shock. That shock comes down and hits the Mach shock again. Now you have the triple point paradox repeated all over again. So down here is what's happening is a shock is coming in, it's hitting the Mach stem, and it's generating another smaller expansion fan, another smaller supersonic patch. And then the whole process repeats itself. And I mean, the reason this was not seen previously is exactly because unless you're really looking for this and you really do extraordinarily high resolution numerics, you just don't see it. It just gets washed out by numerical viscosity or whatever and resolved. So here's just one more picture. So I really love this picture, but it's showing closely spaced U contours. The sonic line is now not included, but here's the instant shock, reflected shock hitting each other, generating this expansion fan. Here's the new shock coming down, generating another expansion fan. Third shock coming down. You know, depending on how gracious you're willing to be down here, there's you know, maybe you could say 4 or even 5 triple points. And is there any questions on that picture or that? Corey, so
Is this experimentally resolvable?
so actually this is experimentally resolvable. So I showed these results in a meeting in ICTAM meeting in Göttingen in the maybe early 2000s. There was a experimentalist there, Derek Hughes, who had a huge South Africa. He had a huge shock tube because mostly in shock tubes weren't big enough to really resolve this. So he actually went back and did some experiments and observed a second triple point in the experiments. So it does seem to be experimental. He then blew up his shock tube because it was so big, it wasn't robust against high pressure experiments. But anyway, so there are experimental observations coming from this.
Yes, an accumulation point for it.
Yeah, so okay, I'll be forthright. My belief is in the inviscid equations, there are going to generically be an infinite sequence of triple points that accumulate at some rear point. Of course, I can't claim any sort of, I mean, it's sort of the transonic phenomenology argument I'll say a little bit about. The transonic phenomenology argument is that you don't get closed smooth solutions, smooth supersonic patches in transonic flows. They have to be terminated by a shock. And this is analogous, which I'll talk about depending on time. Going back to a lot of work that was done in the 50s and earlier on the question of shock-free transonic airfoils. That was a question, could you have shock-free flow over a transonic airfoil? And there are special airfoil shapes for which you get shock-free flows over the airfoils. But the moment you perturb those special shapes, then you'll develop shocks at the rear of so I'll sort of come back to this, hopefully that it's not clear now, it'll be clear in a second. All right, now you might wonder about, does this transonic small disturbance equation really capture what's going on in the Euler equations? I mean, it seems, my experience is remarkably robust. Here's another numerical solution by Alan Sanders, by Alan Testel's collaborators. This is a full Euler solution. So here's the global picture. So now the only difference with full Euler is that now you have this contact discontinuity where there's a jump in entropy and tangential velocity that gets kind of washed out in the TSD asymptotics. And again, very close up, very near the triple point, you see is the instant shock, reflected shock, Mach stem. And again, you see this sequence of patches. So the main difference you see is right here, there's a little kind of jag, and that's coming from when the sort of supersonic patches cross the contact discontinuity. So you don't see that, you don't see this little jag here in the TSD asymptotics. So this is what I was just saying, that there's an analogy between these problems and the question of transonic airfoils. So you take an airfoil here, let's say you have flow coming in at Mach numbers less than 1. The flow accelerates over the airfoil, and then you get this supersonic patch where the flow goes faster than the speed of sound. So out here, it's sort of elliptic subsonic flow. In here it's supersonic hyperbolic flow. So I think actually, like large airplanes, cross Atlantic or whatever, typically fly at a speed where you just get at least some sort of supersonic patch sitting on the wings. And then the question is, can you get smooth flows? Maybe at some point there was some hope, if you took airfoils that gave you completely smooth flow, they might be more efficient than airfoils that had shocks. But I mean, in practice, that's not a robust situation, and you can allow weak shocks at the rear of the patch. So the thing is, again, smooth flows like this are highly unstable. The moment you perturb the shape of the airfoil, you typically will go, let's say you have an airfoil with smooth flow over it and you perturb it slightly, you'll get an airfoil that the flow is no longer smooth. And typically what happens is you'll get a shock at the rear of the supersonic patch that can just come into the airfoil at a normal angle, and then everything is okay, it just terminates there. For these Goodally Mach reflections, of course, you can't terminate the shock. You can't terminate any of the supersonic patches by shock, because that just reintroduces the triple point paradox. So you get basically, that's the complication here in the shock reflection. And the basic idea, going back to Goodally and Buseman and so on, is you look at what's called a Frankel problem. So you have sort of, boundary conditions on the elliptic region out here. Then you have this supersonic patch here, and you're not free to impose boundary conditions everywhere here, because if you impose, again, boundary conditions here, and you sort of have boundary conditions here, you've got a hyperbolic problem, and you're trying to solve a boundary value problem for the hyperbolic problem. And this is trying to illustrate what's called a Frankel problem. In fact, what you can look at is, here's the again, it's elliptic here, hyperbolic here. You have characteristics, two families of characteristics in the, let's say, in the potential flow thing in the hyperbolic region. And the basic uniqueness result says, once you specify the data here and here, and leave this gap between the C1 and C2 on the airfoil, then you get a well-posed problem. But you only get well-posed problem if you sort of leave a gap in the hyperbolic boundary where you don't specify any data. And then everything that happens in here will be completely determined by what happens out here. So if you start with a shock-free flow and then you just perturb inside this region, then you won't get a shock-free flow anymore, because everything is uniquely determined for the smooth flows. Anyway, that's sort of the basic argument by Goodally. And Kathleen Morowitz has a series of papers, 1, 2, 3, on these problems of proving instability of shock-free flows over airfoils. I will just say they are not easy reading. There's a linear paper, and then there's a couple of papers to sort of try and show the nonlinear. The same thing is true for the nonlinear problem. So the frustrating thing about all this is you can do asymptotics, reduce compressible Euler to, let's say, transonic small disturbance equations. But then in many ways, those transonic small disturbance equations are sort of fundamentally no easier to deal with than the original equations. By the way, I should mention, maybe I forgot to mention this, but just a comment. I wrote down these unsteady UTSD equations. If you do dispersive waves, these might be better known as dispersionless KP, because KP equation, you just put KdV in here, UT plus half U squared X plus UXX, and you add exactly the same terms. But of course, you think about KP, you're not dealing with shocks, and the introduction of shocks makes things completely different. It destroys any Hamiltonian structure you have, it destroys integrability. But anyway, that might be a more familiar way to think about it for people in dispersive waves. It's dispersion escaping. And then to simplify further, let's just look at steady flow. So just throw away this UT term and think about steady flows now, steady transonic flows. So that's what I wrote down here. It's sort of, this is the thing where the UT used to be. So you get this pair of equations for U and V. Again, you can think of U as the X velocity, V as the Y velocity perturbed from sonic. And I mean, they look ridiculously trivial, right? And these actually go back to Gödeli, who was doing it in Germany during the war years, and von Karman. And then the Lin-Rees CN unsteady equations, they subsequently put in the time dependence as well. So if you look at this, you can see, for example, if you put U equals phi x, V equals phi y, so introduce the potential, you can see these equations become U phi xx plus phi yy. So these are elliptic when U is positive, hyperbolic when U is negative, and degenerate on U equals 0. U equals 0 is the sonic line where the equations change type from hyperbolic to elliptic. And physically, U negative is supersonic flow. You know, you're perturbing off the exactly sonic flow -1. And then U positive is subsonic flow or elliptic. And it can change type smoothly across the sonic line U equals 0, or you can get what are called transonic shocks, which jump from supersonic state to subsonic state. Now, just to convince you that this is not a simple problem, here's kind of a sketch of a physical picture. Just you have a supersonic jet, Mach number bigger than 1, sort of hitting a high pressure reservoir. And this is a rough idea anyway. And this should be M star in this region. It generates some reflected shock. And in this parameter regime, we're supposing the reflected shock here hits this rigid wall at the top, and it reflects off the rigid wall as a Mach reflection. So this is sort of inverted from the way I had it before, but again, there's a reflected shock here, a Mach stem, and incident shock reflecting off this wall into a Mach stem and a reflected shock with a triple point right here. So that's kind of the general physical picture. And I'm not going to describe any of this, but here's a specific boundary value problem for the TSD equation, steady TSD equation in a rectangle that kind of models that picture. And here's the global numerical solution for that problem. So again, this is the incident shock that's generated from this lower boundary. It undergoes Mach reflection of this rigid top boundary. Here's the Mach shock. Here's the reflected shock. The sonic line is again dashed. So there's a constant supersonic state here, a constant supersonic state here. And the way the boundary conditions are set up, the flow actually re-accelerates to supersonic at the back here. And then there's this large subsonic elliptic region here. So it's convenient to set it up that way numerically, because this is now an outflow boundary, so you don't have to worry about giving any boundary conditions on the left end of the boundary. Because basically the flow is just, it's supersonic here, decelerates to subsonic here, and then re-accelerates to supersonic over here. And in these steady problems, you know, with my sign convention, -x is basically playing the role of a time-like variable in the hyperbolic regions. Now, again, you see here a triple point, or apparent triple point, where 3 shocks meet. And again, that triple point is not consistent with the jump relations. So So here's another blow up by Alan Tesville of what's happening near the, again, in a tiny, tiny region near the triple point. And it looks, you know, this is just a steady version of the self-similar ones we saw before. Instant shock, reflected shock, Mach stem, expansion fan coming here and producing this supersonic region. And then a new shock coming down, a second patch, a third patch, optimistically a fourth patch. Now, one thing to point out, it appears that the triple points appear to be exactly sonic. So these two shocks collide and they collide exactly at a sonic point where the solution's changing type. Now that's not proved, but there's a good reason why that seems to be necessary. Namely, to make the triple point jump conditions work, you need this expansion fan, this fourth wave. But to get an expansion fan, you need things to be supersonic or sonic because it's a hyperbolic type of thing. There aren't expansion fans in the elliptic part. On the other hand, what creates the supersonic region? Well, it's the expansion. This is kind of a chicken and egg problem. The expansion fan creates the supersonic region, and the supersonic region needs to be there for the expansion fan to exist. So it seems to be almost impossible to come up with structures where first the supersonic region forms and then the expansion fan arises. It seems like the only way things can happen is that the expansion fan forms at the sonic point and then pushes out a supersonic region, which then allows the expansion fan. And you know, this is certainly what Gooderly described as well. Now, I mean, one of the questions here is, obviously, how many triple points and patches can occur? You know, are there finitely many? Are there countably infinitely many triple points? And also, could there be a flow with only one triple point and smooth flow behind the Mach stem? So, you know, you just get a nice smooth solution in this supersonic patch that goes back to elliptic. All right, so I'm going to run out of time in a few minutes, so let me just say, one thought is maybe the simplest situation to try and analyze is the one of situation when you have smooth flow. You know, is it possible to have smooth flow here? And that seems much easier to think about than these solutions with multiple shocks and supersonic patches. Now, here's what Gooderly had to say about this. So he, as I said, he proposed this structure of an expansion fan at a triple point and a supersonic patch behind it to resolve this von Neumann paradox. So this is in a technical report in Wright Field Technical Report from 1947. It seems like Gooderly, I mean, he was in Germany during World War II, and it seems like he got snatched up immediately by the Americans after the war as probably the leading expert in the world on transonic flows. And then he has a book on transonic flow in 1962. And so here's what he says in the book. So he says, careful analysis, Gooderly, 1947, this technical report indicates that a singularity results at the rear point of the supersonic patch, or that also in this case, a solution in Tricomi's sense is not possible. That's just a solution that satisfies certain non-singularity conditions. So this is what he says in his book. Unfortunately, it seems to be this technical report seems to have gone completely missing. Costa de Firmus tried to find it at Brown. I know other people that looked for copies of this report and nobody seems to be able to find it. So I don't quite know what careful analysis Gooderly had in mind. But I mean, the question of whether a singularity, and in particular, you know, does a singularity have to form, or is the singularity of smooth flows just highly unstable and non-generic, and maybe it's possible with certain boundary conditions. So I don't know the answer to that question. All right. So should I finish in, is it 50 minutes or what's the time?
Yes.
Yeah. So I'll just finish up. So I won't be able to show you all this stuff, which I kind of expected. But all I want to say is, if you make some assumptions about a hodograph transformation being possible, where you change from uv as functions of xy to xy as functions of uv, these equations reduce to a Tricomi equation. So this is the basic mixed type equation, yu plus uyvv. These, it's exactly similar to that one. But so now y is a function of u and v. And you end up with this sort of Tricomi problem. So the shocks turn into fixed curves in the hodograph plane, which is called shock polars. And it turns out that the shock conditions in the hodograph plane turn out to be oblique boundary conditions on the shock polars. So this picture maybe won't make a lot of sense, but so I mean, this is known for a long time. This is what's called the Boozman porcupine. So this is a shock polar which tells you what states can connect to the state -1, 1. And the black arrows are the direction for sort of Neumann co-normal boundary conditions for that Tricomi equation. The red arrows are the oblique boundary conditions you get behind a shock that's adjacent to a constant state. So anyway, the end moral of this is, assuming you can convert to the hodograph plane, you wind up with sort of questions about uniqueness theorems for Tricomi equation with oblique boundary conditions. And in general, this green line here, this is the expansion fan that turns in. This is the triple point. Because there's an expansion fan at the triple point, it actually turns into a curve. And the basic idea is to show uniqueness for this problem, just the oblique boundary conditions on the shock polars. And again, you need a gap in the supersonic region to expect well-posedness for these Tricomi problems. And once you prove uniqueness here, it's a strong argument, at least, that it's highly non-generic, that you can get smooth flows. That, possibly for very special sort of boundary data here, maybe you end up with a smooth flow, but generically, they're going to be very unlikely. This is actually based on work that a PhD student of mine, Una Chong, did UC Davis a while back, but it's kind of modified for these problems. All I want to say is it's actually quite tricky to, the method is what goes back to Morowitz's work called the ABC method, where you try and construct, or vector field method. So you've reduced this boundary value problem for the Tricomi equation. You try and find multipliers b, yv plus c, u, and choose the construct coefficients b and c for which you get positive definite energy estimates to get uniqueness. And that can be done under certain circumstances. It's actually pretty complicated to go through, and I spent a lot of grief trying to understand the first of Morowitz's papers to implement it. But I'll just say, under certain circumstances, you can indeed conclude that there is a unique admissible solution. So basically, admissible means the solution has to be sufficiently regular that Green's theorem will work for those boundary conditions and so on. And that strongly suggests that a smooth flow behind the Mach shock would be highly non-generic, but it still leaves open the question of whether some specific data could give you a smooth flow behind the Mach shock. So anyway, I'll just stop there. Thanks.
Questions or comments?
Yeah.
Can you go back to the part where you introduced the initial perturbation, adding epsilon u to -1?
Oh, sure, yeah. You mean in deriving the transonic small
Yes.
disturbance equation? One more. Here.
Is there a specific reason for epsilon 3/2?
3 halves there? Yeah, so there is a specific region. It's kind of the classical dominant balance type argument. Namely, you want to balance weak nonlinearity against weak diffraction, right? So if you go to the equation, so if you throw this away, you basically have linear equations. If you throw this away, you basically just get back to the 1D problem. So it turns out that in these transonic flows, the x derivatives are very much faster than the y derivatives. Transonic flows through a channel, for example, they develop a very wide structure because they're almost. So it turns out that what you need in y is you need y derivatives to be epsilon to the 1/2 smaller than the x derivatives. And then that tells you that, in fact, if you balance the size of these things, if u is epsilon, you need the v to be epsilon 3/2. So the basic argument is that scaling is the dominant balance that leads to a balance between nonlinearity and diffraction, weak nonlinearity, weak diffraction, and that's what you need to get non-trivial. Yeah. Yeah.
Do you actually see these phenomena in the lab?
Well, yeah, no, that's what I was saying. So Berek Hughes, an experimentalist in South Africa, actually did experiments after I showed this at a meeting and at least detected a second triple point. But it's certainly true that, they're so small that it's really, really hard to observe. That's why the question was left open for such a long time. And in practice, it may well be that viscosity, whether it's physical viscosity or numerical viscosity, tends to, wash out the whole thing unless you sort of have really large resolution of the flows.
I mean, do you see the actual phenomena or something approaching it?
Well, I'm saying, one of the phenomena is you get these, not just a single triple point, but you get a sequence of triple points.
Okay.
And at least 2 triple points have been observed in experiments. So, but I mean, in some sense, from the practical point of view, it probably is not,
You have viscosity
Yeah, you have viscosity and
then none of this.
well, except I would
Or
say,
Are there some asymptotics that have
well,
put
so I would
in
say, like Riemann problems
viscosity?
in general, what you expect is the Euler solution is going to give you some kind of long time behavior of the viscous solution. And then the question is how long do you have to wait for the path to expand? I mean, that's kind of what you see when you increase numerical resolution. At lower resolutions, everything disappears. Some higher resolution, you maybe see one patch. And as you increase the resolution, then, you see more and more patches, more and more triples. And in experiments, then it's a matter of, can you develop a big enough Mach reflection pattern that you start to see these things?
And I presume that experiments, people who work in airplane design, etc., they must be very concerned about such things. So are there the experiments that are done for such purposes, are they anywhere close to sort of the implicit limit or not?
Well, I will say this, I've seen for example, some people that have done shock tracking algorithms where they try and track shocks, and separately solved in smooth regions. And they had very peculiar results in these regimes because they didn't know how to evolve the triple points. And in fact, they would get solutions where they were supposed to be computing steady flows, and the triple point would keep moving because they didn't have the right, putting in the right structure for the triple point itself. And when they put in these structures, then it worked. So, so that's one case where I know, it was important in, of course, if you're just doing sort of shock capturing, then you don't run into that problem, but they were actually trying to put in the structure at the triple points. Yeah.
Interesting.
Yeah.
Further comments?
So I have a
Yes.
quick question. So these numerical solutions, how much has been improved rigorously?
Well, almost nothing, I would say.
Nothing,
I mean,
so it's
yeah.
just a numerical solution.
Yeah, so that's kind of what I was saying before. That's why, I skipped over the last part of the talk where I was actually trying to do some analysis. But I mean, in some ways, it's what's frustrating about this subject. Since I started it, 1980, you can derive these equations like TSD equations. They look very simple, but in the end, they're sort of almost as resistant to analysis as the full, as multi-D hyperbolic equations. And hence, it's not great that you wind up solving them numerically.
Even with the self-similar answer.
Right, even with the self-similar answer. I mean, they're just, once you get to mixed type conservation laws with shocks and with actual transonic coupling between the hyperbolic and elliptic regions, you're really kind of, I mean, there's probably not much progress since the 1950s in many ways. That's also why I mentioned the Chen and Feldman work. I mean, they did this fundamental work on shock reflection, but the reason they can do it is because it's an elliptic problem, it's fundamental. So they're not dealing with the fully transonic.
So their 2018,
Yeah.
the monograph is still on the elliptic problem.
Well, that's what I'm saying. The regular reflection problem is an elliptic problem because the hyperbolic region a priori. And then it's just a matter of constructing the elliptic solution that sort of matches with, and I mean, it's horrible.
With the free boundary, right?
Well, you have to solve a free boundary, but okay, it's a free boundary value problem for an elliptic equation. You have a degenerate elliptic equation at the sonic line, you have corners, so it's
Nasty, but
it's nasty, but it's not what I consider to be a fundamentally transonic problem.
further comments or questions? Let's thank John again.